Okay, so let me make sure we're seeing. There we go. We left off the last time, last video, talking about confidence intervals, where we had a known population variance, and we were trying to build a confidence interval for where the true population mean was. We can do something very similar when we're looking at a proportion. So maybe I want to know where the population proportion is, and all I have is a sample proportion. Well, we talked about in the last chapter, we know things about the distribution of sample proportions as well. So we said that the mean of our sample proportions will always be the true population portion, or the distribution of our sample proportions are centered around whatever that true population proportion is. It's a mouthful. So we also know the standard deviation of our sample proportions was p times 1 minus p, right? Which would have been kind of like the population variance divided by our sample size. And then if we wanted the standard deviation, we'd take the square root. Now, one thing probably going to run into here is, well, we don't know the population proportion. That's the whole reason we're building this confidence interval. All we have is our sample proportion, so we do our best estimate of what that standard deviation is by using the sample proportion that we see. Okay. From there, it's just like what we were doing with a sample mean, right? Instead of our for the population mean, instead of our sample mean, we'll take our sample proportion. We're then going to add a certain number of standard deviations to get our upper bound, subtract a certain number of standard deviations to get our lower bound. How do we find how many standard deviations away we need to go? Same idea. If I want a 90% confidence interval, alpha, or the area outside my confidence interval will be 10%, alpha of 0.1, 0.1 over 2, no, 0.1 over 2. I want the z-score that gives me 0.05 in each tail, right? So, we're still using the standard normal distribution. Our conventional levels are still 90, 95, 99. We're going to be seeing the same z values that we did when we were looking at population mean examples here. There's this additional requirement. I'm never going to try to like trick you. But we need to make sure that we have a large enough sample size such that n times p is greater than 5. Right? So the number of trials has to be sufficiently large, or also q, or 1 minus p, times that sample size has to be greater than 5 as well. So this is just something like you can't have, like, I don't know, 10 observations if the probability of the success is 0.002, right? But really in practice, it's kind of the steps. It's going to be just like what we were doing for our sample mean. Now, one term I'll start using a little bit more, and we can use this when we're talking about sample means as well. It's probably a little more commonly referred to when we're looking at examples with a proportion. But this thing that we're adding oh, come on. This thing that we're adding and subtracting to our sample proportion, we're going to reference that as our margin of error, right? Here's the sample value we saw. Our margin of error, right, creating this confidence interval around it, is this. Okay. So let's think of an example. So I had some go back to the Affordable Care Act or Obamacare back in 2012. Maybe you ask people, whether or not they were in favor of insurance companies covering people that had pre-existing conditions. So you got 63 out of the 81. You want a 99% confidence interval. What's the true population proportion of people who are in favor of health insurance that covers pre-existing conditions? Okay. Well, what are the things that we need? We need oh, sorry. I put this in between here. So once again, just as a reminder, and I'll show you how we look these up in the table and also Excel, but we're going to find these kind of same benchmark values that we were before. So what are the things that we need? We need our sample proportion, we need our sample size, and we need to know what level of alpha we have now. So there's fewer components than when we're looking at building a confidence interval for a population mean. Our sample proportion, I put 7/9 here. Well, how did I get that? 63 out of 81. 63 out of 81 simplifies down to 7/9 or 0.778. My sample size was 81. If I wanted a 99% confidence interval, that means that there's 1% outside of my interval. In decimal form, my alpha is 0.01. How many standard deviations away do I need to go? Well, or what is my z-score? That gives me not alpha, right, but total of alpha on either side. So half of alpha on each side, 0.005, right? The absolute value of that is 2.58, right? I need to go 2.58 standard deviations above, 2.58 standard deviations below to get my upper and lower bound. From here, I can do the intermediate calculation, so I can find the standard deviation of my sample proportions. Once again, I can't use the true population proportion. I use my best guess. So 0.778 times 1 minus 0.778 divided by 81, take the square root. I now have everything I need to kind of just plug into this very simple equation. Now, I don't always have to do this third step. I can essentially just put this formula down here. Just makes the equation here a little bit longer, a little bit more likely I make mistakes with parentheses or something. So I don't know, just kind of best practice. I typically, and I'll show you this in the Excel video, even when I'm working in Excel, I usually break it down so that I have this calculated in a different cell. Just makes it a little bit easier once we get to kind of building this final step. So here, add my margin of error to get my upper bound, subtract my margin of error to get my lower bound. And I can say with 99% confidence, the true population proportion of people who are in favor of covering pre-existing conditions is somewhere between what, like about 2/3 and 90%, 66% to 90% of the country. That's pretty, it's a lot of people in favor of it, right? And there's a 99% chance the true population proportion is somewhere in this range. Okay. All right, so we got a second example. We'll kind of work through and think about this. So let's say I had 912 registered voters. Oh, what do I want here? I can go back to this. I thought I had a different example. Oh, I guess I switched it out. Never mind. I think this was for the 2016 election. Yeah, 2016 election when Clinton was running versus Trump. So you could set this up for the upcoming election too if you had some sample data. But there was this survey of 912 people, and 46% said they were planning to vote for Clinton. Derive a 90% confidence interval for what the true proportion was. Well, pretty high sample size here. So right away, we should be thinking about the distribution of our sample proportion with a really high sample size. What will that do? Well, as the sample size gets higher, that standard deviation is going to be smaller. We should be able to get a pretty narrow confidence interval here. From there, we've got our sample proportion of 0.46, sample size of 912. Only other thing I need in this example is alpha. Alpha is the decimal form of what's outside my interval. So 90% confidence interval, 10% is outside of it. Excuse me, decimal form 0.1. So here I've got those three things that I needed. I then need to look up the z-score that gives me half of alpha on each side, so 0.05, which going back here, what gives me, oh, actually, I set this up so this is even easier, right? So I wanted what z-value gives me 0.9 in the middle, right? So 0.1 outside of my confidence interval, 1.65 and negative 1.65. Now I could, if I can get my other screen to cooperate here. Give me 1 second. I could have said, okay, well, look, I want 0.05. Where is that in the table? It's like in between these two values, negative 1.64, negative 1.65. I'll use that kind of higher the two, rounded up to 1.65. So positive and negative 1.65 will be the values I use to get my upper and lower bound. I also could have, just as a reminder, we already had all this work from before. I could just use that norm.s.inv. I tell it alpha over 2 or 0.05. It would give me that same value of 1.65 approximately, right? I rounded this or 645. So that's the value that I use, right? The number of standard deviations away I need to go to the left and the right. I'll do my intermediate calculation where I can see that, yeah, when I have a really high sample size, that standard deviation of my sample proportions is pretty small, right? I'm then going to just plug in that sample proportion I found, the z-score that we looked up, and the standard deviation of my sample proportions, add my margin of error to get my upper bound, subtract my margin of error to get my lower bound, And I can see that with 90% confidence, I can say the true proportion of people who were planning to vote for Clinton in 2016 was between 43 and 48, 9-ish percent, right? Or 0.43 to 0.487 being the proportion of people. Okay. So, if there were only two candidates, and then, I would say, I would predict she's not going to win, right? The true proportion was not above 0.5. Now, there's third-party candidates, so we might want to do a step further, right? That same poll of 912 people had 40% of people planning to vote for Trump. So what would the 90% confidence interval be there? Well, we just did a 90% confidence interval, so we're going to be using that same Z value of 1.65. Here, what's the standard deviation of the sample proportion of people going to vote for Trump? Well, take his sample proportion times 1 minus that. Oh, come on. There we go. Divided by our sample size, right? And then add my margin of error to that sample proportion, subtract my margin of error to that sample proportion, my upper and lower bound. So notice here, if I was trying to predict the election with 90% confidence, I could say the true proportion of votes that Trump is going to get is in between 0.37 and 0.4267. Well, if Clinton's lower bound is 0.4328, then I can think about what I've really done here is say, okay, look. Now I forgot the values. Here, I'm going to cheat. Oh, sorry for that. So this is what? 0.3, approximately 0.37, 0.4267. So I know that the true proportion of people who are planning to vote for Trump in 2016 is somewhere in this range. Right? I then said for Clinton, her lower bound was 0.4328 and approximately 0.487. So here, using this sample data, I would have predicted that, oh yeah, the true proportion of people who are planning to vote for Clinton is greater than that of Trump, right? Now, I can only say this with 90% confidence that based off my sample, that looks like Clinton's population proportion will be higher. What if I wanted to say this at the 99% level? Well, what's going to happen? Well, my sample proportions I found are still the same. My sample sizes are still the same, so it's the same standard deviation of my sample proportions. But remember, if I want to go to a higher level of confidence, that's a lower level, so 90 to 95, alpha becomes 0.1, or sorry, alpha goes from 0.1 to 0.01. Half of alpha in my tail is now 0.005. So compared to when I wanted half of alpha to be 0.05, I'm going to be going a higher number of standard deviations to the left and the right to get my confidence interval, or my confidence intervals are going to get wider. Well, notice these are already pretty close. I'm guessing if we worked through the mathematics and we created mathematics, if we worked through the formulas, like plug in, and actually build our 99% confidence interval, it's likely that these are going to become wider, and it's likely now that they overlap, in which case I can't say that the true proportion of people voting for Clinton is greater than Trump, because it could be over here. Trump's could be over here, or Trump's could be over here and Clinton's could be over here. I really can't say with 90% confidence which of these candidates is going to get a higher proportion of the overall votes. Okay. But with 90% confidence, I could, just not with 99. Okay. Right. So I think I've got just some additional examples, and I'm not going to go through these near as slowly. I actually go through them pretty quickly. Just having more information and kind of showing you how we can make predictions using confidence intervals. So I have the exact same setup as the previous two problems. I just grabbed some data from the 2020 election. One thing that could be interesting is once they start getting some stuff out there about who people plan to vote for this next election, you can almost like make the prediction before the election happens. So, one of the problems is with these polls, we talked already about some examples where we might have some selection or non-response bias. But if we believe that we've eliminated some of that bias from our sample, we could use them to kind of make a prediction. So I think I had here 2020 election data. 54% of people said they were planning to vote for Biden. So build 90% confidence interval, same thing. I'm using that same Z value. When I'm looking at the 90% confidence interval, for examples where I've looking at a population mean, or I want to build a confidence interval for a population mean, and I know the population variance, or I'm looking at proportion examples, I'm always going to use that same Z value for the 90% level. I then plug in my sample portion, sample size, add my margin of error, subtract my margin of error to get my upper and lower bound. And the proportion of people who are going to vote for Biden here was between 51 and 56%, approximately. So this would have said, well, yeah, we can predict he's probably going to win this upcoming election. And then if we looked at Trump, they had 43%. We could do the same thing. We could do something very similar. Excuse me, where we build the confidence interval for Trump at the 90% level. Once again, these confidence intervals don't overlap. So if there's no overlap, we could say that the true population proportion for Biden was going to be higher. In fact, that's what ended up happening, right? Now, if I want to do the 99% level, my confidence intervals become a little bit wider here, but I don't know, there's a pretty good gap in between Trump and Biden here, right? 0.45 being the upper bound, 0.51 being the lower bound for Biden. So it's another example. I also went out. This is interesting. So here was one poll. Here's a second poll that had 47%. If we use this poll, notice, well, of this higher number of this higher sample size, building still a 90% confidence interval. This one, here's the confidence interval for Biden, 0.48 to 0.53. For Trump, 0.44 to 0.49. So notice the upper bound for Trump's confidence interval just above the lower bound for Biden's. So this would have been inconclusive. I really couldn't have said using this sample with 90% confidence that the true proportion of people who are going to vote for Biden was higher. So you can do this for any election, right? But this is, I think, a pretty obvious application of building these confidence intervals and then using them to say, okay, look, does this, is this true population proportion greater than this other true population proportion? And political scenarios seem like an obvious application of that. Okay. All right. So that should kind of cover it for proportions. I think I'll save this Excel stuff. This will be a standalone video. So we'll look and see a little bit more in depth how we do this in Excel as a standalone video. Right now, I'm just working through some of these problems with you. So we'll skip through these for right now. We're now going to talk about the more realistic scenario, which is that if I wanted to build, so we're switching away from proportions again, going back to sample means. So if I wanted to build a confidence interval for a true population mean, but all I have is my sample mean, but if I don't have the population mean, it seems likely that I'm probably not going to know the population variance either, right? So what do I do, right? Most of the time, we're not going to know that, right? Most of the time, we can't figure out what that population variance is, and so I can't calculate the variance of my sample means or the standard deviation of my sample means. So what do I do? Well, what do I, kind of similar to the proportions, what's the best guess that I have of what the true population variance is? I just use the sample variance. Now, we kind of use slightly different notation here because this kind of is, okay, here's what's the sample, or what's the sample standard deviation of my sample means, right? But this is just indicating that I wasn't using a known population variance, but some sample variance, okay? Now, if I'm using a sample variance, because I don't have all of the population data, what we're going to do is and we won't walk through all the mathematical proofs as to why, but if I'm only using a sample variance, there's going to be a distribution for that as well. And so it's not going to be the same as the true population variance. And so when I create z-scores, they're not actually going to be standard normally distributed. Right? So what do we need to do? Well, I mentioned this before with that Gassett guy who came up with the, what was the discovery we talked about earlier? oh, he did some of the normal distribution stuff, but he more specifically came up with these student t distributions because they didn't have any formal training. They just kind of gave him this word of student or the names of student as opposed to like the normal distribution. Sometimes it's called the Gaussian distribution. So student t distributions, I really should have a kind of plural, is every single sample size. If I'm only using my sample variance, well, think about it. How did we calculate a sample variance? Part of it was in the denominator, we had n minus 1. Well, that's going to, even if I found exactly the true population variance with my sample data, when I calculate it, I'm not going to be dividing by n, I'm dividing by n minus 1, so it's always going to be a little bit higher. The sample variance will always be a little bit overinflated, even if it was exactly the same as the true population variance, right? When I'm calculating, I won't be dividing by n, dividing by n minus 1. So it's going to be a little bit more spread out than my standard normal distribution once I kind of turn different values into a z-score dividing by now this sample standard deviation of my sample means. So a little bit more spread out, but still symmetric, right? Still looks pretty, it is a normal distribution. It's just not a standard normal distribution. Right? Now, I mentioned, as we looked at how we calculate the sample variance, n minus 1, we're going to be further off, right, when we have small sample sizes because dividing by 2 instead of 1, or sorry, 1 instead of 2 dramatically changes the value of your fraction, but dividing by 99 instead of 100 doesn't change it as much. So for these higher sample sizes, or these we end up calling, they're directly related to this degrees of freedom, which degrees of freedom is just n minus 1, right? So kind of lines up with thinking about we're calculating the variance by n, dividing by n minus 1. As I have a higher sample size and a higher degree of freedom, these student t distributions get closer and closer to a standard normal. In fact, I think I have on this slide. Yeah, there we go. Once I get to 100 degrees of freedom or more, I can't tell the difference between the two. Like it's out to such a far decimal, how what they're going to be off by. So really, any degrees of freedom over 100, we can use that standard normal distribution as an approximation. Right? But for lower sample sizes, lower degrees of freedom, I'm going to have to use this set of distributions or these student t distributions. Right? So they're still symmetric. I already mentioned that. A little more spread out. And if we can get a large sample size, we can just use a standard normal to approximate. All right. So actually going to, forgot to open this up. So give me 1 second. Maybe. Tables. Okay. Apologize for this. I thought I had it pulled up, but now I'm not seeing. There you go. Sorry about that. So here's my t tables that we're going to end up using. Right? So before we go to there, just to kind of point out, so this is what my student t distributions look like. We're going to have a different distribution for every degrees of freedom. So here would be my standard normal distribution. Right? If I had a student t distribution where my degrees of freedom was 20, it's going to be a little bit more spread out. So it's still symmetric around 0, right? But it's going to be a little bit more spread out, meaning that it's more likely that I see values that are further from that mean of 0. If I then looked at degrees of freedom of 5, even lower, it's even more spread out. Right? So if I think about now when I'm building confidence intervals, when I had the standard normal distribution, well, I just went 1.96. Actually, let's see. 1.96 standard deviations above and below, and that gave me 0.025 in the tail. The problem is if the area to the right of 1.96 is 0.025 here, what's the area to the right of 1.96 when my degrees of freedom is 20 for a student t? It's a much larger area. So notice if I keep using the same value, the same number of standard deviations that I'm going to build my confidence interval to the left and the right, now the area to the right of 1.96 is not 0.025, but 0.062. And then if I go to an even lower degrees of freedom, now the area is even greater, right? So I can't keep using the same values I was from the standard normal distribution where we had a known population variance, or we're looking at a sample proportion, trying to build a confidence interval for a population proportion. Now I'm going to have to use different values, right? I can't keep using 1.96, and the value that I'm going to need to use is going to be different for every degrees of freedom, okay? So what does my t-table look like? I'll show you a truncated version, and then I'll show you the PDF version I'll have up on Canvas. And I'll also show you how we use Excel, which is what I would probably say you should get used to and default to. But here's my different degrees of freedoms, right? Now I said, once you get up to like 100, notice when I want the area in the upper tail of 0.05, the normal distribution value, right? Or if we had truly an infinite number of degrees of freedom, should be 1.65. It's 1.66. Should be 1.96. It's 1.98. Like we're off at the second decimal by a little bit, but it's getting pretty close, right? After 100. So here's our different degrees of freedom. The way that we use this table is say, well, first of all, here's the standard normal values. But the way I would use this table is, okay, let's say my degrees of freedom is 50, and I wanted to build a 90% confidence interval. Well, that means there's 10% outside the interval, or 0.1. That's my alpha. Divided by 2 is 0.05. So at a degrees of freedom of 50, the value that gives me 0.05 in the tail is 1.96, or sorry, 1.68. I'll show you the larger version of the table, right? So, this doesn't have every alpha value, but it has some of them, right? Kind of our conventional ones, right? Alpha divided by 2 of 0.005, 0.025, 0.05. So, and then it has degrees of freedoms, basically 1 through 100. It starts making larger jumps here, but notice, I mean, I get to 1,000, like even at the third decimal, these don't really look at hardly any different. So anything over 100, we say we can use it as a pretty good approximation. We could just use these standard normal values. Another thing that's nice about this student t-table is you can use this last row where the degrees of freedom is infinite. These just represent those standard normal values. So notice if I want the z value that gives me 0.05 in the tail for a standard normal, that's 1.645. 0.025 in the tail, standard normal value, 1.96, and so on and so forth. Okay. So you can use this table, and I'll pull it up and we'll kind of use it as we're working through examples. Or you can also use Excel, right? So I'll put these on the separate one. That doesn't really matter. So let's say I wanted to find t values that I'll go with 90, 95, 99% levels, right? So here's my different like conventional levels of confidence. Alpha values associated with that are going to be what? 0.1, 0.05, and 0.01. What's the t value? It's going to give me half of alpha in each tail. Right? Well, I know the area that I want in the tail is alpha over 2, but I have like two tails. I have two sides of my confidence interval. So if I tell it alpha over 2, notice it's going to be a small area. I'm always going to find the negative. It's just like we were doing before. We'll always find the negative value. So instead, what I'm going to do is just take the absolute value, of whatever t value I'm getting. Well, how do I find the t value? This is where instead of norm.s.inv, I'm going to use t.inv. Actually, here, I don't know, my caps lock was on. So t.inv, the area that I wanted in each tail is half of alpha, comma, what's my degrees of freedom? Well, here this would be based off of the sample size. So let's say the sample size was 35. My degrees of freedom would be 34. So this t.inv is going to tell me at a degrees of freedom of 34, what t value, how many standard deviations away do I need to go to get half of alpha in on each side of my interval? And then I'm just going to take the absolute value so I can just kind of think about the, I'm using that value when I'm plugging it into my confidence interval equation. So notice, copy this down, and these values vary a little bit from our standard normal values. In fact, we could actually put them side by side here. Norm.s.inv, if this was a standard normal, half of alpha, and I forgot to take the absolute value. Yeah, close my parenthesis for me. Oops. Excuse me. These numbers are a little bit different. Okay. All right, so that's how we do it in Excel. We'll work through a couple examples, but really it's the same setup that we had before. It's just that now to calculate that standard deviation of our sample means, we only are using our sample variance, not a population variance. And instead of using a z value, we're going to be using a t value, still associated with half of alpha on each side of the interval. And our degrees of freedom will be n minus 1, sample size minus 1. So what are the general steps? This looks very similar to what we were doing before. What gets the only thing different? I'm using these t-distributions, sample variance here. The structure is still the same as what it was before. Okay. So let's say I'm going to give this an interesting example, but just to put some numbers to see how this looks like, and then we'll kind of look at some more interesting examples. So let's say I draw 36 observations from a population, and I find a sample variance of 324 and a sample mean of 9. What is the confidence interval that corresponds to an alpha of 0.01? So once again, I'm trying to show it in different ways so we can work in both directions. But if I have an alpha of 0.01, that's going to be a confidence interval at the 99% level, right? 0.99 is within the interval, 99%. Okay. So what are the things I need? In my sample mean, my sample size, my sample variance, those were all given to me. And in this one, I was actually directly given alpha as 0.01. So I then need to find, okay, what's the t value associated with not alpha, but half of alpha, so 0.005 at a degrees of freedom of 36 minus 1, so 35. So what could I do? How do I find this value? Well, there we go. I was a little bit off, right? Our degrees of freedom is 35, right? I didn't want it for the alpha of 0.1, but actually 0.01, so 2.7238, or rounded the second decimal, 2.72. If I looked at the student t table, degrees of freedom of 35, right? I wanted 0.005, so 2.72, sorry, 2.724. Okay. So I've got my t value associated with the degrees of freedom of 35 and giving me half of alpha on each side of the interval. I then could do an intermediate calculation if I wanted to. I could also have just plugged this in down here as well. And I'm just writing this in different ways, right? So remember the square root of the variant, the square root of something squared is itself. So I could take the standard deviation over the square root of the sample size if instead of giving, if the problem gave me the sample standard deviation instead of the sample variance, maybe this equation is a little bit easier, this format. But I can actually calculate what that is. Then it kind of saves me a little bit. I've only got 3 numbers here. I got to worry less about parentheses and order of operations. So to get my upper bound, I'm going to be adding 2.72 times that standard deviation of 3. Lower bound, I'm going to subtract that margin of error. Here, I've got a pretty wide confidence interval, right? So yes, I saw a sample mean of 9, but with 99% confidence, the true population mean could be anywhere in this range of 0.8 to 17. And why? Well, A, we wanted a pretty high level of confidence. So we're going to have to go, quite a few standard deviations to the left and the right. Our standard deviation is relatively large because that variance is of the original, we found that sample variance we found is pretty large. And our sample size wasn't that great. All right. So moving forward, and just to kind of show you how we usually display this, we calculate the upper and lower bound. We then kind of in brackets say, here's our lower bound, here's our upper bound. That's our confidence interval. Let's think of another example. let's say the American Medical Association says the mean salary for all physicians is $175,000. You're like, seems pretty high. So you take a sample of 81 physicians and you find a sample mean of 160. You still have a really large sample variance, so 324 million. What would the confidence interval be for the true population mean at the 5% level? So this is where I'll kind of show you how I would kind of maybe set this up in Excel, or you could set up something in Excel to kind of like be a calculator for even future problems. So it's going to be very similar to what I showed you for when we had a known population variance. So I'm just going to copy this, paste it. So everything's going to be the same, except here I'm only going to have my sample variance. We don't have any of these values yet, and we're going to get rid of this. Okay, we're no longer using z values, but we're using student t values. Okay, so the sample mean that we found was what, 160,000. Sample size was 81 physicians. And I said what, 324, 231, 23, 324 million was our sample variance. So just looking at how high this variance is, what's probably going to be true about the range of our confidence interval? It's going to be pretty wide, right? So here I'm just going to do the intermediate calculation. So I'm going to take the square root of my sample variance over my sample size. This should give me the standard deviation of my sample means, right? But I'm using, the sample standard deviation of my sample means because I'm not using a known population variance. So then you need to go, okay, how do I find these t values? Well, once again, I could do the absolute value, right? T dot INV, right? And I want the area of alpha divided by 2 in my tail, comma, what's my degrees of freedom? I could type in 80 here, but if I wanted to use this for future problems where I just plug in different values, my degrees of freedom will simply be my sample size minus 1. Now, when I copy this down, I do want my alpha to update, but I never want my sample size reference to change. So I'm going to freeze that reference, Command T on a Mac, F4, or your function F4 key on a PC. And I'm going to copy this down, right? Now, really here, I didn't have to delete these functions because they're going to be exactly the same as what I had before. I'm going to take my sample mean. I'm going to then subtract this many standard deviations. And then what is my standard deviation on my sample means? Right here. Okay. Now, I'm then going to think about when I copy this. It's actually here. If I were to copy this down, what don't I want to change? Well, I do want my t-value to change, but the sample mean value I'm using, no matter what level of confidence that I'm building, is always going to be the same. And that standard deviation of my sample means will always be the same. So I can go ahead, copy this down. I've got my lower bound for 3 different levels of confidence. Now my upper bound, if I copy this over, it's going to I'll show you. It's a problem, right? Because, oh, well, I didn't want it to update. So, I could freeze it and then unfreeze it, or I could just say, look, take this, Command C or Control C on a PC, hit enter, go to the cell you want to paste it in. When you copy paste this way, it doesn't update any of the cell references. The only thing I want to change in my upper bound is I'm no longer subtracting my margin of error, but I'm adding it. We're then going to kind of drag this down. I've now got 3 confidence intervals very quickly. Now I could go through and use the table, right? I could look up my sample size was 81, so I could look up that degrees of freedom of 80. I was building I already forgot what the problem wanted now. 95%? Yeah, alpha of 0.05, so I wanted a 95% confidence interval. So 0.05 was alpha, but I've got half of alpha in each tail, so 0.025. So 0.025 at 80, 1.99. Sure enough, that's what I found in Excel. Okay. So just kind of showing you how we would do in Excel. You could also really just plug away at this by hand. You would use the exact same, process and formulas. It's just, I don't know, in my mind, it's a little bit more work. It's a little bit easier to set this up in Excel. Yeah. So this is kind of laid out step by step how you would solve it. If you didn't do it in Excel, you'd have to use that table that we just did to find that t-value of 1.99. Intermediate calculation, you get the standard deviation of our sample means is 2000. Now it's just a matter of plugging those things in. Okay. So, if I think about this example, if the American Medical Association said that the average was 175,000 for a physician, I can look at them and say, well, based off of my sample data with 95% confidence, I can tell you that no, it's not. Because the true population is somewhere with 95% confidence. I can tell you it's somewhere in this range. Okay. Oh, and then kind of one final thing, and then I'll make a separate standalone video where I just go through more examples in Excel with some actual data, is what we talked about in the last chapter applies to every single one of these types of examples. So whether it's a population mean where I know the population variance, I'm building a confidence interval for a population mean and I know the population variance. I'm building the confidence interval for a population proportion, or I'm building a confidence interval for the population mean when I only have a sample variance. If we ever have that the sample size over the size of our population is ever greater than 0.05, that was where we said if we have a large proportion of the population in our sample, we might have to use this correction factor. So this correction factor, basically updates kind of what our standard deviation is of our sample mean or our sample proportion, but the equations will look exactly the same as what we've worked through. It's just that when you look at that standard deviation, it gets multiplied by this correction factor. Well, we said this correction factor, n minus n over n minus 1, will always be something less than 1. So when I apply the correction factor, this will actually make my confidence intervals a little more narrow, which is just, I shouldn't say it's a good thing, but it's good in the sense that I'm able to narrow down, a smaller number of values that the true population mean or proportion could be. So when I work through the Excel examples, I'll throw in some additional like, oh, we need to check to make sure that this is true. Or sorry, that this isn't true. If this is true, we have to use this additional correction factor. We have a little more work to do. Okay. And I'll never try to kind of trick you with this, like, oh, ask you for the confidence interval and just hope you realize that the ratio here is above 0.05. But I might give you an example where I say, assume that you have this sample size and this is the population, you know that it's greater than 0.05. Now, using your correction factor, right? So I'll kind of point out that you need to use it, right? All right, so the remainder of these slides are going to match up with what we do in Excel. So I'll have a standalone video where we look at how we do each one of these types of examples in Excel. Sample mean, where I only have a sample variance, sample proportions, sample means where I know the population variance. Okay.